Assalamu alaikum. I am Jahangir Alam, lecturer in physics. I welcome you all in my online class. First of all, thanks to Almighty that He has given me the ability to take this class, and still I am carrying on my regular activities. Dear student, I also hope all of you are well by the mercy of Almighty and carrying on your regular studies, staying at home. Dear student, in our today's class, we are going to discuss some important topic from physics second paper and first chapter of physics second paper, right? And our today's topic is capacitor, capacitance, combination of capacitance, and some mathematical problems related to capacitor. Right, dear student? I also hope you will be benefited from our today's class, because this portion or the topic to be discussed in our today's class is very important for your exam. So let's start our class. Right, dear student, actually capacitor is a device or electronic device in which we can store charge as energy. Okay, in maximum of the electronic devices we are using in a day in our home, like radio receiver, remote, electronic toys, electric fan, we are using capacitor, right? The shape and size of capacitor may vary according to their requirement. So dear student, so it is an electronic device where we can store energy as electric charge. So definition of the capacitor can be defined as capacitor, the mechanical process to store charge in a conductor called capacitor, right? Dear student, this is a device where we can store energy as electric charge. Dear student, now we can see the basic mechanism of a capacitor, that is how a capacitor can be charged or discharged, that is the charging and discharging of a capacitor. So dear student, if we consider these two are two conductor or conductor plate placed side by side, and they are separated by a insulator, right? And one plate or conductor is connected with the positive pin of a source or cell, and the other end of the source or cell connected to the other conductor. Since normally these two conductors are electrically neutral, when this plate is connected with the negative pin of the cell, then the negative charge from the negative pin of the source will be accumulated in the plate, as well as we can see there are negative charges accumulated by the source in the negative plate. And on the other hand, since the positive end of the cell is connected with the other plate, so negative charge will be repelled by this negative charge in the first plate. On the other word, we can see that the positive pin of the battery will be it will attract the negative charge from this plate, and when the negative charge or electron will repel by this negative charge of this plate, the negative charge or electron will be repelled or displaced from this plate, and as well as the positive charge will be appeared in the plate. So from this way we can say that the charges are conserved or charges are set or stored in this two plate. So in this way we can store charge as energy, right? So dear student, this is the charging process, that is in this way we can charge a capacitor according to further use or according to use in our requirement. Now if a charged capacitor is connected to any electronic device like this, then there is a potential difference between the two plates of the capacitor, and according to the law of flow of electricity, the electric current will pass from this plate to this plate, and electron will pass from this plate to this plate. As a result, the device will be active. Right, dear student, this is the charging and discharging process of a capacitor. Dear student, now we'll see another important term related to capacitor, and that is capacitance, right? So to realize capacitance, we need to see the figure. Suppose the two plates of a capacitor are connected with a source whose potential difference is V, right? And as a result, the first plate will plate that is connected with the negative pin of the battery will be charged negatively, and the plate connected with the positive pin, the source, will be charged positively. If the charge stored in the negative plate is denoted by Q, similarly the amount of charge in the other plate will be plus Q, that is negative Q. If the potential difference is more, then the accumulated charge or stored charge will be more. So from the concept we can say that accumulated charge or stored charge in a capacitor is directly proportional to the potential difference applied on it. So from the concept we can write that Q, that is stored charge, is directly proportional to V, right? So dear student, if we replace the proportional sign by a constant, we can write Q is equal to C into V. Here C is a constant of proportionality. This constant is known as capacitance of the capacitor. Okay? So dear student, we can write C is equal to Q by V. So from this expression we can give the definition of capacitance. Okay? So from the expression we can say that the amount of charge required to increase the potential of a capacitor by unity is called capacitance of the capacitor. So the definition of capacitance is given here. The amount of charge needed to increase the potential of a capacitor by unity is called capacitance of the capacitor. So from this expression we can write that when V is equal to 1, then we can write that C is equal to Q. So this is described in the statement, the amount of charge Q needed to increase the potential of a capacitor by unity, that is when V is equal to 1. This means by unity is called capacitance of the capacitor, that is when V is equal to 1, then the amount of charge will be equal to C, that is the amount of charge in a special condition, that is when V is equal to 1 is called capacitance of the capacitor, right? Now we can see the unit of capacitance. So from this expression we can see that the capacitance of a capacitor is depends on Q and V. So from this expression C is equal to, if the unit of charge is coulomb, C divided by volt, right? In short form we can write that C by V or C per V. This is the unit of capacitance. So C per V or coulomb per volt is known as farad. So according to the name of a scientist, the unit of capacitance is called farad. So this is the SI unit of capacitance, right? Dear student, from this expression we can say that 1 farad is equal to 1 coulomb per volt, right? So definition of 1 farad can be defined as 1 farad is equal to 1 coulomb per volt, right? From this expression we can get the definition of 1 farad, that is, if 1 coulomb charge is required to increase the potential of a capacitor by 1 volt, then the capacitance of the capacitor is called 1 farad, right? It is also an important definition. Okay, dear student, so you need to memorize the definition of 1 farad. I state again that if 1 coulomb charge is required to increase the potential of a capacitor by 1 volt, then the capacitance of the capacitor is called 1 farad. I hope you got it. Dear student, now we'll see the symbol of a capacitor. That is how we can represent a capacitor in our electronic circuit. If two equal bar placed side by side and connected by two wire is represents a capacitor. That is, this is the symbol of a capacitor. It is almost similar to the symbol of a cell. In the cell there are two bar, but in the cell one bar is longer and another bar is smaller. The longer bar represents the positive pin, the smaller bar represents the negative pin. This is the symbol of a cell, but this is the symbol of a capacitor, right? In capacitor both bar are equal. Right? I hope you got it. My dear students, now we are going to see the combination of capacitors, right? So before that, first we need to the equivalent capacitance, right? To realize the combination of capacitance, we have to know first the equivalent capacitance. The equivalent capacitance can be defined as the capacitance of a capacitor used instead of any combination. That is, there are two types of combination. One is series combination and another is parallel combination. So the use instead of any combination of the capacitors is called equivalent capacitance of the combination, right? So dear student, here is a combination. Here are three capacitors are connected in such a way that the negative plate of first capacitor is connected to the positive plate of the second capacitor. Similarly, the negative plate of the second capacitor is connected to the positive plate of the third capacitor. So this type of combination is known as series combination. So in our previous classes we have learned about the series combination of resistance. You know, if resistance are connected in such a way that this type of combination of resistance is known as series combination. Similarly, this type of combination of capacitor are known as series combination, right? So dear student, in series capacitance or series combination, if the applied voltage in the combination is V, so the applied voltage will be divided in across three capacitor. If the voltage fall or potential fall across the first capacitor is V1 and that across the second capacitor is V2 and that across the third capacitor is V3, then we can say that the applied potential V will be equal to the summation of V1, V2 and V3. Now, right, from the definition of capacitance we can write that C is equal to Q by V. So if we apply this expression for the first capacitance, so we can write that C1 is equal to Q by V1, right? So dear student, from this expression we can write that V1 is equal to Q by C1. Okay. Similarly, for the second capacitor we can write that V2 is equal to Q by C2, and for the third capacitor we can write that V3 is equal to Q by C3, right? Again, we know V is equal to V1 plus V2 plus V3. Okay, if we use the value of V1, V2, V3 from the previous expression, we can write V is equal to Q by C1 plus Q by C2 plus Q by C3, right? Or V is equal to Q multiplied by 1 by C1 plus 1 by C2 plus 1 by C3. Okay, this is equation number 1. Dear student, if the combination of three capacitor is replaced by a single capacitor so that the applied voltage and charge will remain same, then the single capacitor, that is the capacitance of the single capacitor, will be known as the equivalent capacitance of this capacitor. So in this case, if the equivalent capacitance of the combination is denoted by CS, so we can write that CS is equal to Q by V. Here, according to the definition, the stored charge and potential difference will remain same, right? So from the expression we can write, so V is equal to Q by Cs. This is equation number 2. So from equation 1 and 2, we can write that the Q by Cs is equal to Q into 1 by C1 plus 1 by C2 plus 1 by C3. So simplifying from or omitting Q from the both sides, we can write that 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is the required expression for the equivalent capacitance of these three combinations. So in this way we can determine the equivalent capacitance, that is the equivalent capacitance of series combination for the more number of capacitor, right? Now we can see another combination of capacitance. If the capacitor is connected in a such a way that all positive plates of a capacitor connected to a common point and all negative plates are connected to another common point, then this type of combination is known as parallel combination of capacitor, right? This type of combination is known as parallel combination. So in parallel combination, so applied voltage V is applied to positive ends of the as well as the negative ends. So here potential difference across each parallel plates will be same. So according to the definition of capacitance, we can write C is equal to Q by V. So here we can write Q is equal to C into V. So for the first capacitor, if we use this expression, we can write Q1 is equal to C1 multiplied by V, because here potential difference V is common for each capacitor. Similarly, if we use this expression for the second capacitor, then Q2 will be C2 into V and Q3 will be C3 into V. Again, from the basic of this combination, we can write if total charge is Q, then Q is equal to Q1 plus Q2 plus Q3. So if we use the value of Q1, Q2, Q3 from the above relation, we can write Q is equal to C1 V plus C2 V plus C3 V, right? Or Q is equal to V multiplied by C1 plus C2 plus C3, right? This is equation number 1. Now if we replace this combination by a single capacitor, so that the total charge and potential difference remain same, then the single capacitor will be the equivalent capacitor, or the capacitance of the single capacitor will be the equivalent capacitance of this combination. Here, if the capacitance of the equivalent, that is if the equivalent capacitance is Cp, then we can write that Cp is equal to Q by V, or we can write Q is equal to Cp into V. This is equation number 2. So from equation 1 and 2 we can write Cp V is equal to V multiplied by C1 plus C2 plus C3. So omitting V from the both sides, we can write Cp is equal to C1 plus C2 plus C3 and so on. So this is the required relation or expression for the equivalent capacitance in parallel combination, right? So dear student, these are very simple expression as we have learned about the parallel combination, series combination of resistance in our previous classes. But you have to mind it that the expression for the parallel combination in resistance is reverse to the parallel combination of capacitor. Okay? Dear student, now we are going to some mathematical problem related to our discussed topic in our today's class. So first mathematical problem said that the equivalent capacitance when two capacitors are connected in parallelly is 5 microfarad. That is, there are two capacitors when they are connected in parallel combination. The equivalent capacitance is 5 microfarad, and when they are connected in series, the equivalent capacitance is 1.2 microfarad. Find their capacitance. Right? So individually we need to find the capacitance of the first capacitor and second capacitor. So dear student, we don't know what the capacitance of the two capacitors are. Here, let the capacitance of the capacitor are C1 and C2, right? If the capacitances are C1 and C2, then according to the definition, when they are connected in parallel, that is, the equivalent resistance of the parallel combination Cp is equal to 5 microfarad, and when they are connected in series, that is, the equivalent resistance of series combination is 1.2 microfarad. So we need to determine C1 is equal to what and C2 is equal to what, right? So dear student, from the previous discussion we have discussed in our today's class Cp. If the Cp is the equivalent capacitance of the parallel combination of C1 and C2, so from the expression we can write that we know Cp is equal to C1 plus C2, right? Is equal to, the value of Cp is equal to 5 microfarad. So 5 microfarad. Again, when they are connected in series, so we know 1 by Cs is equal to 1 by C1 plus 1 by C2. If we take the LCM of C1 and C2, so we can write C1 C2 over C1 plus C2, right? So the value of C1 and C2 from the previous relation we can write 5 microfarad divided by C1 C2. Again, you know the value of Cs is equal to 1.2. So 1 by 1.2 is equal to 5 microfarad divided by C1 C2, right? So if we use the value only, so we can write C1 C2 is equal to, if we multiply 5 with 1.2, then it will be 6, right? So if the equation, this equation is 1 and this is equation 2. So from the equation 1 and 2, if we find out the value of C1, then from this expression we can write C1, if we replace C2 from this expression, so we can write 5 minus C1 is equal to 6. That is, since C1 plus C2 is equal to 5, so C2 is equal to 5 minus C1. So from this expression we can write 5 C1 minus C1 square is equal to 6. Or we can rearrange the equation C1 square minus 5 C1 plus 6 is equal to 0. Or from the concept of the solution we can write C1 minus 3 into C1 minus 2 is equal to 0. That is, C1 is equal to 3 or 2, right, dear student? So the capacitance of the first capacitor will be 3 microfarad or 2 microfarad. When C1 is equal to 3 microfarad, then C2 will be 2 microfarad, right? Since we know the summation of C1 plus C2 is equal to 5 microfarad. When C1 is equal to 2 microfarad, then C2 is equal to 3 microfarad. So from this expression we can say that the capacitance of the two capacitors are, therefore the capacitance of the capacitors are 2 microfarad and 3 microfarad, right? So dear student, I hope you got it. Dear student, now we will see another mathematical problem which is described by a circuit diagram. In the circuit diagram there are 3 capacitors. They are connected in a complex combination. You know, the C2 and C3 are connected in parallel and C1 is connected with the series of the parallel combination. And different type of question may appear depending on the circuit, and the probable questions may appear on the basis of the circuit diagram. I have mentioned some of them here. First question, it may be that what is the equivalent capacitance? That is, we need to determine the equivalent capacitance of this complex or compound combination. Then they can ask you that what is the charge stored in each capacitor or total charge stored in the circuit diagram. Then they can ask you that the potential across each capacitor, and finally they ask you that the energy stored in the each capacitor. Though we did not discuss about the expression for the energy stored in a capacitor, you will see the expression for the stored energy in a capacitor in our next class, but I am going to show you the probable question that may appear on the basis of this circuit diagram, right? So dear student, first we are going to find the equivalent capacitance of this combination. Okay, so first we need to realize the what are the capacitors which are connected in parallel. Here C1 and C2 are connected in parallel and C1 is connected in series with the parallel combination. Okay, so first we need to determine the equivalent capacitance of C2 and C3. Solution. Here C1 and C2 are connected in parallel. So if the equivalent resistance of C2 and C3 is Cp, so we can write Cp is equal to C2 plus C3, right? So here C2 is equal to 3 microfarad plus C3 is equal to 2 microfarad. So the equivalent capacitance will be 5 microfarad. That is, the equivalent capacitance of this combination is 5 microfarad, and this C1 or 5 microfarad is connected in series with this parallel combination. Now if total equivalent capacitance is Cs, then 1 by Cs is equal to 1 by C1 plus 1 by Cp, right? So here 1 by C1 means 1 by 5 plus Cp means also 5, 1 by 5. It will be 2 by 5. Therefore Cs is equal to 5 by 2 or 2.5 microfarad. This is the equivalent capacitance of this combination, right? I hope you got it. So Dear student, so equivalent capacitance of this circuit already we have calculated and the value was 2.5 microfarad. Now we are going to determine the potential across each capacitor. So to determine the potential across each capacitor, before that we need to determine the charge stored in the total circuit, right? Or charge stored due to the combination. So here we know from the definition of capacitance, we know C is equal to Q by V, right? So we can write Q is equal to C multiplied by V. So here the total capacitance of this circuit already we have determined here. Cs is equal to 2.5 microfarad. Here you need to convert the value into SI unit because we are going to show the relation between QC and V. QC and V. Since this is the relation of different quantities, so we need to convert the value into SI unit. So if we would like to convert the value into SI unit, it will be 2.5 into 10 to the power minus 6 farad. And here the value of V, the applied voltage V is equal to 10 volt. So stored charge or total charge stored due to the combination will be C 2.5 into 10 to the power minus 6 multiplied by 10. So it will be 2.5 into 10 to the power minus 5 coulomb. So this is the total charge stored in the combination, right? Now we are going to determine the potential across each capacitor. Here C1 and the combination of C2 and C3 are connected in series. So if the total voltage is V, then if the voltage across C1 is V1 and that across the combination is V2, then V1 plus V2 will be 10 volt. But from the definition of capacitance, we can write C is equal to Q by V, or V is equal to Q by C. So if we would like to determine the value of V1, that is the potential across C1, then we can rearrange this equation. V1 is equal to Q by C1. So for the first capacitor, if the potential across the C1 is V1, so we can write V1 is equal to Q by C1. So using the value, Q is equal to 2.5 into 10 to the power minus 5 divided by C1. The value of C1 is equal to 5 microfarad, and if the value is converted to SI unit, it will be 5 into 10 to the power minus 6 farad. Okay, and after the calculation you will get 5 volt. So this is the voltage dropped across the capacitor or first capacitor, that is across C1. Similarly, the voltage across the combination, since C1 and C2 are connected in parallel, so voltage across C1 and C2 will be same, right? So similarly we can determine the value of V2. Okay, so I hope you got it. So similarly we can calculate V2. V2 is equal to Q by, here V2 is the potential across the parallel combination. So here C will be CP, parallel combination, equivalent resistance of parallel combination. So Q is equal to 2.5 into 10 to the power minus 5, and the equivalent combination of this equivalent capacitance of this combination was 2 plus 3, 5 microfarad. So 5 multiplied by 10 to the power minus 6. So it will also 5 volt, right? So in this way we can determine the potential across each capacitor. So 5 volt. This 5 volt is the capacitor across both C2 and C3, since these two capacitors are connected in parallel combination. So potential difference across two combination are the same, right? Dear student, I hope you got it. Dear student, now we are going to determine the charge stored in each capacitor. That is, what amount of charge is stored in first capacitor, in second capacitor, in third capacitor. So from the expression we know C is equal to Q by V. So or Q is equal to C into V. So if we use this expression for the first capacitor, so stored charge is denoted by Q1, then it will be C1 multiplied by V1, right? Since we are going to determine the charge in the first capacitor, so here C will be C1 and V will be V1. So therefore, so Q1 charge is stored in first capacitor, C1 is equal to Q1 is equal to C1 multiplied by V1. Okay. So here C1, you know the capacitor, a capacitance of the first capacitor is 5 microfarad, and it will be 5 into 10 to the power minus 6 farad multiplied by V1. You know, in our previous calculation we showed that the value of V1 was 5-fold. 5. So it will be 2.5 into 10 to the power minus 5. The unit will be coulomb, right? This is the charge stored in first capacitor. Similarly, if we determine the charge in the second capacitor, right? So we need to determine the value of Q2. Q2 is equal to C2 multiplied by here V2. So V2 is applicable for C2 and C3. So V2. So you know the value of C2 is equal to 3 into 10 to the power minus 6 farad multiplied by value of V2 is equal to 5-fold, right? And after the calculation you will get 1.5 into 10 to the power minus 5 coulomb, right, dear student? This is the amount of charge in the second capacitor. Similarly, charge in the third capacitor will be Q3. Q3 is equal to C3 multiplied by V2, because V2 is applicable for C2 and C3. So here value of C3 is equal to 2 into 10 to the power minus 6 farad multiplied by V2 is equal to 5 volt. So after the calculation you will get 1.0 into 10 to the power minus 5 coulomb. So this is the charge in the third capacitor. Okay. Now finally we are going to determine the energy stored in each capacitor. So the question may appear in like that: total stored energy or energy stored in each capacitor. First I will show the total energy stored in the combination, then I will show the energy stored in individually in each capacitor. If we determine the energy stored or total energy stored in the combination, I have already mentioned earlier that we did not show the expression for the energy stored in our today's class, but you will get it from our next lecture, the energy stored. So energy stored in the capacitor is, if stored energy is U is equal to half C V square. This is the expression for stored energy. So if we determine the total energy stored in the capacitor, then we can use for our today's circuit, it will be U is equal to half C. C means CS, then V square, 1 by 2 CS. You know, total equivalent capacitance of our today's circuit that we have calculated in our previous calculation. It was 2.5 into 10 to the power minus 6, right, farad, and V here total potential is 10, so it will be 10 square, and after the calculation it will get, you will get 1.25 into 10 to the power minus 4, and unit will be joule. This is the total energy stored in this circuit. But if you, so In the same way, you can determine the energy stored in the first capacitor, in the second capacitor, in the third capacitor. The energy stored in the first capacitor, if denoted by E1, then it will be 1 by 2 C into V1 square. The energy stored in the second capacitor, it will be half into C into V2 square, and similarly, energy stored in the third capacitor will be half into C3 into V2 square. Right? So, dear student, I hope you got it. So no more today. So thank you very much being with me in my class. May Allah bless all of you. Assalamu alaikum.